This is lecture 4A for Calculus 1 on the Taylor series. The Taylor series is a method to approximate a function with a polynomial. Well, actually, the Taylor series is the result, but this is the method to find the Taylor series. And what the Taylor series is a polynomial that approximates a function. There are several steps. First, you need to pick a strategic point. I'm going to call that x naught. Then I'm going to write out this polynomial, and I'm going to write it out in descending order. So here's my polynomial. In descending order, it would have a constant term, then a linear term, then a square term, and then here's my cubic term, x raised to the fourth, x raised to the fifth. Now we're used to polynomials being written like this, constant term if we wrote it in descending order. Then a1 times x, a2 times x squared, a3 times x cubed, a4 times x to the fourth, etc. And this is exactly the same, except instead of x, we write x minus x naught. Remembering x naught is just a number. It's just the strategic point. So you actually could write all this out and combine it so it looked like this, but it's very handy in this form, and this is how we start. So I've got to get this down. Okay, so here is the polynomial. It has a constant term a naught. It has an a1. Okay, it's got a constant a2 multiplying the squared term. It's got a3, a4, etc. All right. All of these multiply the x's, and we write them as x minus x0, x minus x0 squared, x minus x0 cubed, x minus x0 to the fourth. Right, that's the start. So what do we have to do to make this polynomial match up with the function? We have to pick values for a0, a1, a2, wherever it is, a3, and we've got to pick those values. Now we have a scheme for picking those values that works really well. Here is the scheme. We assign values to the coefficients by comparing the values and derivatives of the function to the values and derivatives of the polynomial. So if we want this polynomial to model a function, at x naught we want it to have the value of the function. Okay. We want the first derivatives to be the same. We want the second derivatives to be the same. We want the third derivative to be the same. And we can keep going on like that as far as we need to. Actually, these are infinite series. Sometimes, though, you don't need all the terms. The more terms you have, the more accurate it is, and I'll show you that too. So what we're going to do is try to find values, or we will find values for the coefficients, a0, a1, a2, a3, a4, by using the value and derivatives of the function and comparing them to the value and derivatives of the polynomial at the chosen point. Obviously, we'll start with the constant term a0. We have to have that. Let's say that at x naught, our chosen point, we want the polynomial and the function to agree. It wouldn't make sense to have an approximation that doesn't even start at a point that you've chosen. It's got to match up with at least one point. So let's say it has to match up at x naught. So our polynomial, we want it to equal the function at x naught. Well, let's put x naught into this polynomial and see what we get. And now you see why we went x minus x naught. See how clever that was. So I'm evaluating the polynomial when x equals x naught. So remember, this term was x minus x naught. Now it's 0. How about this one? This is 0. This is 0. This is 0. This is 0. All of them are 0 except that first constant term. So the polynomial at x naught is a0. And we want that to equal the function. So now we have a value for a0. It is the function evaluated at x0. And that is, as I showed above, because all terms except that leading coefficient dropped out when I evaluated the polynomial at x naught. Now let's try to find a value for a1. We do that by requiring that the first derivative of the polynomial equals the first derivative of the function at x naught. So we're matching values, and now we're just going to start matching up functions. Let's look at the first derivative. If I take the first derivative of that polynomial, the a0 is gone because it was a constant. So I have an a1. This was squared, so I got 2a2, and then x minus x naught, 3a3 times x minus x naught squared. I just took the derivative of a polynomial. So all of those exponents came out front, and the exponents decreased by 1. That's it. Okay. If I evaluate that at x naught, then all those x's, let me get that, all these x's become x naught because I'm going to evaluate right at the chosen point. When I do that, all these terms that I've outlined here, that I've highlighted here, are going to go to 0. And all I'm left with is the a1. This is all that's left. Everything else goes to 0. So the derivative, this should have an x naught on it. The derivative of the polynomial evaluated at x0 is a1, and I said that better be equal to the function, the derivative of the function at the same point. So now I have a value for a1. So a0 was the value of the function at x naught. a1 is the value of the first derivative of the function at x naught. We have to keep going because it's not that easy. Some numbers sort of start creeping in here. So now I'm looking for a value for a2. I find that by requiring that the second derivative of the polynomial at x naught equals the second derivative of the function at x naught. So if I take the second derivative, remember there was an a1 term from the first derivative, that's a constant, it's gone. So now if I take that second derivative, I end up with, I'm going to go back and show you what I'm taking the derivative of so you can see it. Okay, this is the first derivative. If I want the second derivative, I take the derivative of this. Well, this is a constant, so it's gone. Okay, so it'll go. I'll X that off. Here was the next term, and it was a linear term, so we'll end up with 2 times a2. If I take the derivative of this, the 2 comes out in front, so I've got 2 times 3 times a3. The 3 will come out in front, and I'll get 3 times 4 times a4. The 4 will come out in front. This 4 right here will come out in front. I'll get 4 times 5 times a5. Okay, so that's what you're going to see in a minute. I'm taking the derivative of this function that I've kind of written all over. Okay, so here was the result. The a1 is gone. Here was that 2 times a2. Now, remember the 3 came forward, or 2 came forward, and I have 3 times 2 times a3, and it's multiplying x minus x naught. Then I had 4 times 3 times a4, multiplying now x minus x naught squared. So I'm just taking successive derivatives of these. Go practice it sometime, and you'll just see. It's so easy, it's incredible. All right. If I evaluate this at x naught, all these terms in parentheses will end up being x naught minus x naught, or 0. And all I end up with, all that we're left with, is this leading term, which is now 2a2. So I say the second derivative of the polynomial, when evaluated at x naught, is equal to 2a2, and I say that better be equal to the second derivative of the function there. I want the value for a2, not 2a2, so I have to divide by 2. So here we go. a2 is half of the second derivative of the function. Now let's look for a value for a3. We do that by requiring the third derivative of the polynomial equal the third derivative of the function. So I'm taking the third derivative of the polynomial, and I end up with this constant term, which I'll put in green here, 3 times 2 times a3, which we had from before. And now we have all those others that are still sort of hanging around, and all of them will end up with terms x minus x naught in them. If I take and evaluate this derivative, this third derivative, at x equal x naught, everything in yellow will go to 0, and all that's left is 3 times 2 times a3. So here's that result right here. The third derivative evaluated at x naught equals 3 times 2 times a3 times the third derivative of f. right? I want a3, not 2 times 3, so I have to divide that out. So a3 equals 1 over 3 times 2 times the third derivative of f evaluated at x naught. So now we're going to continue this pattern, matching all the derivatives. If I want the value for a4, I match the fourth derivatives. If I want the value of 5, I'll be matching the fifth derivatives. If I want the value of a6, I'm matching the sixth derivatives. But remember, a term like a6, right here, was originally in front of x minus x naught raised to the sixth. So I had to differentiate it a whole bunch of times before I got to the sixth derivative, and that's why all these numbers are under here. 6 times 5 times 4 times 3 times 2, essentially times 1, or 6 factorial. So here's the pattern. The coefficient a4 equals the fourth derivative of the function divided by 4 factorial. The fifth derivative of the function, the fifth coefficient a5 equals the fifth derivative of the function divided by 5 factorial. The sixth derivative, or I can't say that right, can I? The sixth coefficient, a6, equals the sixth derivative divided by 6 factorial. And here it is in general. The nth coefficient, a to the n, in that polynomial equals the nth derivative of the function divided by n factorial. Well, that's a pretty easy way to evaluate all those constants in the Taylor polynomial. Now we're going to put all this together. First, let's look at the original polynomial. There was an a0, then there was an a1. They have been different colors. Oh, what other color do I have? Here's an a2. Okay, so the value for a0 was the function. The value for a1 was the first derivative. The value for a2 was the second derivative over 2 factorial. Okay, so we had a3, and that is the third derivative of the function divided by 3 factorial. This is the Taylor series right here. Let me erase everything. Okay, so this is the Taylor series. It is a polynomial in x. The constant term is just the function. The first term is the first derivative of the function times x minus x naught. The second coefficient is the second derivative of the function divided by 2 factorial times x minus x naught squared. The third coefficient is the third derivative of the function divided by 3 factorial times x minus x naught cubed. A very nice pattern. So the nth coefficient for the nth term is the nth derivative of the function divided by n factorial times x minus x naught to the n. Okay, once you see that, it's pretty hard to mess it up. So with that, we're going to develop the Taylor series expansion for sine x about the point x naught equals 0. So right about 0, we're going to develop this sine expansion. So we need to evaluate everything at x equals 0. So here we go. For a1, we needed the function. The function at x0 is sine of 0, which is 0. Now we need the first derivative, which is cosine, evaluate it at x equals 0 and get a 1. Now we take the second derivative, which is just minus the sine of 0, gives me another 0. The third derivative is minus cosine, evaluate at 0, get a minus 1. This has a pattern, as you can see. The fourth derivative, you get sine back, so you get a 0. The fifth derivative, you get cosine again, now you get a plus 1. Right. So I'm going to substitute those in for, this will be my a0, this is my a1, this is my a2, this is my a3, this is my a4, this is my a5, this is my a6. Okay, so we're still working on the series expansion for sine x about the point x equals 0. And I put the original polynomial here again so you can compare. So a0 is supposed to be 0. Okay. a1 was 1. a2 was 0, so I just wrote a 0 for it. a3, the function was minus 1, but you have to divide by 3 factorial. For a4 you had a 0, so I just zeroed it out. For a5 you had 1, but it has to be divided by 5 factorial. a6 is 0, etc. So here's what it looks like. The polynomial expansion of sine x is x minus x cubed over 3 factorial plus x5 over 5 factorial minus x7 over 7 factorial, and it continues. So, because we're representing sine of x, we can write sine of x is, well, actually, this is the expansion. You have to do a lot more work to prove that it really converges as you go to higher and higher terms. But right now, you should be able to develop a Taylor series and know how it's going to work. I'm going to use sigma notation. Okay, here's my sigma. N is going to go from 0 to n, minus 1 to the n. That will give me my sign changes. Plus 1, minus 1, plus 1, minus 1 that I need. X to the 2n plus 1. Why? Because 2n plus 1 is a way, if I start at 0, to get all the odd numbers. So that gives me the odd coefficients, and then that appears also as a factorial in the denominator. You can cut off the Taylor series wherever you want. If you just use the first derivative, that is called the linear approximation. Right? The more terms you use, it's a higher order Taylor series. If you use like the first 4 derivatives, that's called a 4th order Taylor series. Okay, here's the result. The red line is the sine of x. That's the function we were trying to approximate. And we're trying to approximate it about the point x equals 0 right there. So for the Taylor series, everything matches up right there. The derivatives, all the derivatives, and the function value. If you only use the first derivative, you get the linear approximation. It's a first order Taylor series approximation. That's the blue line. You can see it actually is okay for a while. Well, maybe through here. Then you can see the gap developing and you see how bad it is. If you add 7 terms, look what you get. Isn't that amazing? The green. Okay, here's the 7th order. It's green. It matches, well, not quite a complete cycle, but it does a very good job of matching that sign for, well, just about, a little over a cycle, using 7 terms. And you can use as many as you want. The more you want, the more you have, the more that Taylor series approximation will fall right on top of the sine curve. All the transcendental functions have Taylor series already worked out and published. They're usually developed about x not equals 0. Sometimes they're called the Maclaurin series if they're developed about x equals 0, but most people just call them Taylor series about x equals 0. You can use the terms interchangeably. Here's the cosine. Do you remember sine had all the odd powers of x? Cosine has all the even powers, but it looks similar. X squared over 2 factorial, x to the 4th over 4 factorial, and the signs alternate, plus minus, plus minus, plus minus. Here's e to the x, about x equals 0. It has every term all added together. It starts with 1 plus x squared over 2 factorial plus x cubed over 3 factorial. Any point could have been used. The approximation will just be the best at the particular point you choose. So we're going to show an example now of approximating e to the 3x about the point x equal 1. So we have to evaluate the function at x equal 1 and get this value. Then we have to take the first derivative, second derivative, third derivative. Then we plug it into that formula. Okay, p of x, the value of the function. So the value of the function goes here for the a0. The first derivative is a value for a1. The second derivative is a value for a2, but it's divided by 2 factorial. The third derivative is here, divided by 3 factorial to supply a cubed, or a to the third. So all I've done here is a third order Taylor series approximation for the function e to the 3x about the point x equal 1. So I can write e to the 3x is approximately, and then I'll write out this series. Okay, I've only used 3 derivatives, and you can see the result in a minute. Okay, so here's the result. In red is the function e to the 3x. The linear approximation has only uses only the first derivative, the function and the first derivative, the first 2 terms. Here's the linear approximation. You can see it works okay, very close to x equal 1, but as soon as you get too far away, not even up till 2, look at the error. Here is that third order Taylor polynomial that we worked up before on the previous slide. It's very close for quite a while. Now you start to see some error developing right here, and of course it falls away here. So that was the Taylor series approximation. I don't separate out the linear approximation from the Taylor series. The linear approximation is just what you get by using only the first few terms, the first 2 terms of the Taylor series. So I'm going to go back and show you the equations again and quickly show you the method. After that, hopefully it's clear. So we start with a polynomial that looks like this. x0 is the chosen place where we want to evaluate the function. We want the polynomial to match perfectly at the point x0. So we write out the polynomial like this. The polynomial will have coefficients a0, a1, a2, a3, a4, a5, etc. We find values for all those coefficients a0, a1, a2, a3, a4 by requiring that the polynomial equals the value of the function at a0 and that all the derivatives also match up. Because we've taken multiple derivatives, we end up with these numbers in front of a to the 4th, and we have to divide those out. So in general, the nth coefficient equals the derivative of the function, the nth derivative of the function evaluated at x0 divided by n factorial. And here's the result. This Taylor polynomial equals the first term, a0 is the function. This a1 is the first derivative. a2 is the second derivative divided by 2 factorial. a3 is the third derivative divided by 3 factorial, etc. The nth derivative, the a to the n, is the nth derivative of the function divided by n factorial. The Taylor series, there's no end to it. It has an infinite number of terms in it, but you stop at some place that's computationally feasible if you're doing this numerically. And however many derivatives you've included, that is the order of the approximation, a third order Taylor approximation, a fifth order, a seventh order Taylor series approximation. The more terms you include, the better the approximation for more values of x. Here was the example for the sine of x. If you only include the first derivative, it's called a linear approximation. It agrees completely well with the function right at the point where you made the approximation, and for how long it agrees with the function depends on how nonlinear the function is. If the function is highly linear, then it will agree for a long time. If it's not linear, then it doesn't agree for very long. The more terms you use, here this is seventh order, you get better agreement for a longer time. This is a Taylor series approximation about x equals 0. And here's the Taylor series to the function e to the 3x about the point x equals 1. If you only include the first derivative, that would be the first 2 terms, you get the linear approximation. You see it matches up right at x equal 1, and for a little, I don't know, it's okay in a certain neighborhood. In this case, it's not. It doesn't take long before the linear approximation falls away from the actual function. But even taking the third order, that would include the constant term and the first 3 derivatives. So it's only 4 terms to that polynomial. Look how much better agreement you get.